Hello, my name is Chanyeok Park, and today I'm going to present a paper called Context or CNN, which was published at CBPR 2020. This paper tries the object detection task in static cameras leveraging long-term temporal context, especially to animal camera traps and traffic cameras. Before we can talk about the idea, let's go throughout the static cameras first. Some examples of static cameras are animal camera traps or traffic cameras, which are shown below in the picture. Unfortunately, static cameras have some different characteristics compared to moving cameras or videos. First, the viewpoint of the camera is always the same. And secondly, it collects sparse data over a long time, and most of them are useless data. For example, in the case of animal camera traps, a deer pops up at the camera for a short time and disappears. Most of them are just landscapes, which are useless data. And lastly, it contains long temporal consistency. For example, like a city bus showing up at every 4 p.m. in the traffic camera. These characteristics usually makes the detection task hard, but the paper proposes, what if the model can learn to leverage the long temporal context regardless of sampling irregularity and apply them to object detection? Long temporal context can be like, for example, periodic behavior of animals in animal camera traps or scheduled city buses at traffic cameras. Unfortunately, there are some challenges that static cameras have in object detection. First, objects of interest are partially and irregularly observed because the camera cannot move. Secondly, due to the environmental factor like fog or night, the observed images can have poor quality. And lastly, the background, like the red box shown at the third image, can distract our detector to detect them as objects while they are not. Now, let's see how the paper models their network. This is the pipeline of the network, which is really simple. The network takes some adjacent frames from the keyframe and gives them to faster RCNN, which most of you will already know. Then the extracted features go throughout two attention networks with residual connection. Each of the attention incorporates the information from the memory, which helps the second faster RCNN to predict correct results. Note that the attention block does not have any novel ideas compared to the paper. Attention is all you need. Then let's look at the short-term memory in depth. Short-term memory is just a neural network that incorporates temporal context of several frames. As you can see at the figure, it takes the features of adjacent frames and it's learned end-to-end with the network. When inferenced, it attends to important features in the short-term memory and gives it to the keyframe features by just adding it. Now, let's look at the long-term memory. Similar to short-term memory, long-term memory is also a neural network. But compared to short-term memory, long-term memory cannot learn the features by end-to-end learning because long-term memory incorporates thousands of frames which will be computationally interruptible to calculate the backprop algorithm. So instead, we go throughout the target dataset or other datasets like COCO and pre-train the long-term memory to extract and store the important features in. To sum up, the long-term memory incorporates temporal information of thousands of frames and use attention to select the important feature, just like short-term memory. And long-term memory is pre-trained and remains frozen throughout the training. Let's see how the experiment results show. We use three datasets, which are Snapshot Serengeti denoted at SS, and Caltech Traps at CCT, and CityCam at CC at the results. Let's first look at the quantitative results. At A, we can see that our model outperforms single-frame detector in all datasets. Also in B, we found that Snapshot Serengeti dataset incorporating longer context information helps the model to learn better. At C, it shows that different strategy of pre-training long-term memory, and the results showing the target dataset was best for selecting the memory. At D, we can see that it's beneficial to use both short and long-term memory. Qualitative results show that attending long context information is also useful. The green number is the weight of the attention, which shows that using long-term context helps with detection at the keyframe. Also, our network is able to overcome the aforementioned challenges, which are better than single-frame models. In conclusion, we saw that static camera setting, attention-based temporal context boosts our network performance, and our model is also adapted and robust to challenges such as irregular frame and environmental factor and static questions. Thanks for your attention.